The presentation is visible.
Yes, sir.
Okay.
Sorry, sir, for waiting. Still another 4 minutes we'll wait, sir.
Yeah, sure.
Yeah, good evening, sir. So, uh, Subhashini madam, are you there? So, can you introduce today's speaker?
Yes, sir. Good evening, sir. Myself, Subhashini, from ECE Department, Brilliant Engineering, Technology and Sciences. Welcome to this FDP session, sir. We are honored to introduce Dr. Abhijit De, Senior R&D Engineer, Accord Software and System Private Limited, Bangalore. Abhijit De received the PhD degree in Electrical and Electronics Engineering from the Birla Institute of Technology and Science, Pilani, India in 2023. He received the BE degree from the Department Electronics and Communication Engineering, North Maharashtra University, Jalgaon, India in 2011. The master's degree in radio frequency and microwave engineering in 2014 from 2017 to 2019. He was a junior research fellow of the ISRO founded project with the Birla Institute of Technology and Science in 2021. He was a visiting scholar with the Department of Aeronautical and Aviation Engineering, the Hong Kong Polytechnic University, Hong Kong, SAR, China. He is currently a senior R&D engineer with Accord Software and Systems Private Limited. His work covers a wide spectrum of satellite navigation technologies, including high precision RTK positioning, multi-path migration techniques for urban and obstructed environments, GNSS timing modules for synchronization critical applications, robust algorithm development for position enhancement under degraded signal conditions. In addition, his research interest includes signal processing in software-defined GNSS receivers, INS GNSS integration, ionospheric scintillation privilege, and migration techniques in GNSS systems. And it is our privilege to have him with us today to share his valuable knowledge and insights. Thank you, sir. I request you start the session, sir.
Yeah, thank you, madam. And thank you, Dr. Naraya, for inviting me for this faculty development program. And I would like to share a little bit about the GNSS signal processing. I hope this whole session will be helpful for everyone. Yeah, so I would like to start. So my presentation is visible, right?
Yes.
So just let me know that whether the slides are getting changed. It's changing?
Yes, sir.
Okay. So I think it's late 6 o'clock in the evening. So good evening, everyone. So the introduction has been already given. So I'll not waste time on that and directly jump into the discussion. So my today's agenda of the presentation would be in and around on this GNSS signal processing, where I will be covering the overview of GNSS positioning, software defined radio technology for GNSS receiver, then the architecture of the software receiver, then timeline of GNSS SDR development, how these many years it has evolved, then the sticking signal structure and baseband signal processing. Also, I will try to provide some useful resources where if someone wants to start looking into this field of GNSS, where to start, what are the resources freely available in the open sources, that all things I will be trying to cover in this presentation. And finally, I'll use this platform to also introduce my company portfolio, where presently I'm working. Okay, starting from the fundamental of satellite-based navigation and timing. So satellite-based navigation and timing has become the predominant technology for positioning and timing with the billions of users and almost infinite number of applications. A variety of passive techniques where equipment only receives and does not transmit includes radar and its equivalent at other wavelength, whereas in this technology the external sensors estimate an object's location by measuring the propagation time and Doppler shift of a signal reflected from the object with a known speed of propagation, and finally communicates its position and velocity to the object. Next is the Doppler ranging, which is also the fundamental base of our first satellite based system known as transit, where the receiver estimates its position by measuring the Doppler shift over time of a signal transmitted by the satellite having a known orbit. And this is also the technology which will be used for our LEO positioning. So low Earth orbit satellite tracking will be done based on the Doppler. So we are going back where we actually started satellite navigation. Third one is triangulation, where the receiver estimates its position by measuring the angle of arrival of the signal transmitted from a known location. Next is multi-trilateration, also known as MLAT. It is a generalized form of trilateration, which is the fundamental principle of GNSS positioning, and also widely known as hyperbolic positioning, where receiver estimates its position by measuring the time difference of arrival of synchronized signals transmitted from pairs of known locations. Multiple pairs of known locations will be there, and most of the signals are synchronized to each other. So those signals are used to compute the position or the geolocation. And finally, the trilateration, where the receiver estimates its position by measuring the propagation time of signal transmitted from unknown location with a known speed of propagation. When I say known speed of propagation, I mean speed of light. So this is a very specific case of MLAT. So trilateration is also the basis of GNSS. So I think that this part has been already covered by another resource person, but still I will just give an overview, brief overview of the segments present in GNSS. So basically we have three segments: space segments, control segment, and user segment. Space segment consists of the satellites, all the satellites which are orbiting. They ranges between 19,000 to 3,600 kilometers away from the Earth, and different constellation like US based GPS is there, then our own Indian Navik is there, then Beidou, the Chinese, then Japanese QZSS, then Russian GLONASS is there. So all these come all together forms the GNSS constellations. They all come under the space segment. Control segment is that which comprise the ground based network of master control station as well as data uploading stations and monitoring stations. So what exactly the control segment's job is to monitor the health status of the satellites. All the uplink and downlink related to the satellites are done by the control segments. They are ground-based segments. Finally, the user segments, which is nothing but our mobile phones, the receiver, which uses the signals which is being transmitted from the satellite. So through a picture I have tried to make it very clear over here. So we have the space segment, which is nothing but your satellite, and we have a control segment which is a bidirectional communication is happening where uplink and downlink both are present. However, in the user segment, which is the receiver, which will only receive the signal. What kind of signals it will receive? It will receive the information about the satellite position and time. Using those two information only, we have to compute our position. So let's say the user segment has received that signal and it has successfully decoded the information, which a GPS signal has transmitted. Okay, so in my presentation, I will take only one constellation as a reference. So I'll stick to GPS. So all my numbers, whatever I will be presenting, will be with respect to GPS satellites. So once it has been decoded the information from GPS, so he can compute two things basically. One is the three-dimensional position of the satellite and the time at which the signal was transmitted. This is also known as the time of ephemeris or the satellite time. Secondly, the satellites are way above from the sky. Thus, GPS signals, when GPS signal is received, it would be delayed by some time. So that is the fundamental principle of GNSS positioning also, because it has transmitted at the time TS. Assume that it is transmitted at TS time. By the time it has received the receiver, it has some delay. So that delay basically used to find out the distance between the satellite and receiver. So let's say the receiver at the ground has a real-time clock. It has to maintain one real-time clock, and that using that real-time clock, it will understand that at what time it has received the signal. By using this time and our satellite transmitted time, which he will be able to decode from the broadcasted signal, he will trying to find out the distance between the satellite and receiver. If you multiply the difference with speed of light, you will get the distance range. So this is the fundamental principle of GNSS. So through a picture, I have tried to make it clear. So here you can understand that the transmitted signal has been done at a particular time, and by the time it has received at the receiver, there is some delay, time delay. So that time delay is basically the distance, which is indirectly indicating the distance between that. Now coming to the measurement. So what kind of measurements? We understood that okay, there is some time delay. By means of that time delay, we are able to geolocate ourselves on the earth surface. Now what kind of measurements basically a receiver will try to use to compute a position? So there are three typical type of measurements which are used in GNSS receiver. First is your pseudo range, which just now we have discussed. Other one is the carrier phase measurement, and third one is Doppler. So pseudo range is basically the same, the distance between the receiver and receiver clock at the signal reception and the satellite clock at signal transmission, scaled by the speed of light. Now definitely the clock which is being used by the receiver and the clock which is being used by the satellite, they are not the same. So we will come to that point also, that what is the problem, what are the problems associated by the clock differences. Carrier phase measurement is nothing but the instantaneous beat phase values, phase difference values, and the accumulated number of zero crossing of the full cycles. So it is the accumulation of Doppler range, or indirectly we can say that it's an accumulated form of a Doppler range. So from the time the tracking starts, once you have locked to your signal, how many full cycles it has covered, that information plus the change in the phase, that forms the carrier phase measurement. This is also an direct way of calculating the range information, and they are compared to the pseudo ranges much more precise. Why? Because it is being generated from the instantaneous beat phase differences. However, in the pseudo ranges, it is completely associated with the time difference. So if you have a time difference of some microseconds, there will be a discrepancy of some meters of error. Finally, last one is the Doppler. So this Doppler is basically the relative change in the frequency, because when it is being transmitted from the satellite at some carrier frequency, let's say L1 frequency 1575.42 megahertz, it is not only that frequency which you will be able to capture at the receiver. It is the relative motion between the satellite and the receiver, which where the change in frequency will get introduced. So that is the Doppler. So it is the L1 plus FD will get added. So if we are able to track the Doppler, this Doppler frequency is basically used to find out, calculate the velocity of the receiver. So we understood that the pseudo range, carrier phase, and Doppler observations provide the basic measurements for computing position and velocity, as well as the offset of the receiver time with respect to GNSS system timescale. So this is all about the measurements. This we will we'll discuss more in details in the later stage of when I will be discussing on the signal processing part. Now, basic range based positioning is, as I have already said, there is a time difference between the satellite and receiver that scaled by the speed of light would give you the pseudo range. Why pseudo range? Because it is not the true range, it is the pseudo range. It's not the actual range difference, because there is a discrepancy between the time of both satellite and receiver. However, just to clarify that, the clock error associated with the satellites are being always transmitted as a part of navigation data. So you will also get an information when you are decoding the navigation data that what is the error in the clock in terms of the satellite. However, the receiver clock, the inaccuracy or the discrepancy or the drift of the clock, you need to estimate and then you have to correct it. So let us take a very hypothetical situation where it's not we cannot say it's a practical situation, but very hypothetically I can assume that, let's say, the clock of the receiver is synchronized. The receiver clock and the satellite clock, they are ideally exactly identical, apple to apple comparison, and assume that there is no atmosphere. Means when I say there is no atmosphere, means I'm talking about vacuum kind of thing. So if there is no atmosphere, there is no delay which is getting introduced in your signal. Third one is there is no measurement noise itself. So there is no random perturbations to the measurements, which in a practical realistic scenario, it is more likely to happen. So in this situation, this ideal and simplified circumstance, what should be your measurement equation? So it would be basically the distance between the satellite and receiver. So it is nothing but the Euclidean distance between the satellite and receiver, because there is no other error in between that. So this is basic distance formula, where you can see that this is the vector of your receiver, which is unknown to you. Unknown position vector of the receiver antenna, possibly moving and therefore a function of time. So it will be changing with respect to time. Second one is your satellite position, the navigation message transmitted by the satellite. So one more thing, when we say that navigation data consists the information about satellite, it means that it is not the direct satellite positions which is being transmitted in the navigation data. It is the information which is required to compute the satellite position. However, the time is directly fed there. So both the vectors are referred to an earth center, earth fixed coordinate frame, uh, with a with a single range measurement, we would say, which is nothing but this point. If you have this measurement from only one satellite, we would know that the position of the receiver antenna must lie somewhere on a sphere, right, and centered on the satellite with a radius equal to the measured range. So you can see that you consider only the first circle or the sphere where the satellite 1, it is centered there, and the radius of that circle is nothing but the measured range. So with only one satellite. Now, if we add one more satellite to that, the intersection of these two would comprehend you that where exactly you are located, but still you are not able to find out the exact point, because still the uncertainty is too much. So to support that, let's say we add one more satellite range information, which is row 3 from a third satellite, which intersects these two circles at 2 points. So the one which is closest to the earth surface would be your 2 point, other one would be straight away discarded from that. So simultaneously, measurements of ranges of 3 satellites is sufficient to determine a position fix in 3-dimensional, at least in principle. right? But is it like practically how much it is possible or not, that we will discuss in the upcoming slide. So this is the same demonstration where the trial iteration method has been explained, that there is one satellite. So probably the radius would be the range, measured range from one satellite. And this is the two satellite, two spares intersection. So your uncertainty has reduced. So in this case, you might be, the first case, you might be somewhere on the, you know that, okay, with that distance, somewhere on the spare you are, right? But you don't know exactly in the which part of the spare you are. Second satellite will tell you a little bit more clarity. The uncertainty will decrease. Similarly, when the third satellite gets introduced, the uncertainty is even reduced, and you can actually locate that where exactly you are point. To explain this in a very simple manner, I have one more example. So let's say uh, you are 3 kilometers from person's A's house. So all you know that you are on a circle 3 kilometers from person's A house, right? Now, if you also know that you are 4 kilometers away from person's B house, so this X and Y is the possible location where you might be, because you have these intersection of these two circles are X and Y. So somewhere in, you might be in X or you might be in on Y location. So let's say if we add one more circle, and you know that you are 6 kilometers away from person C's house, then all these three circles wherever they intersect, that is the point of your actual location. So that is known as trial iteration. But that's not all, everything, right? Because as I said, the user clock time may not be accurate enough. There might be some discrepancy in the clock of the user, because uh, most of the receivers will use a low cost clock. However, in case of the satellite, the clocks are atomic clocks and they are highly precise and more expensive. So they are more precise in nature compared to the clocks which are used in the receiver. So there will be an inaccuracy. There will be a drifting nature of the clock. The age of the clock will matter. The rate at which the clock is drifting will matter. So as I said, that the distance is calculated by the time delay multiplied by the speed of light, right? So the time delay, so the time delay at the receiver is being calculated, the receiver time is based on your clock only. So if that, let's say there is an inaccuracy, let's say an offset of only 1 microsecond. If there is an 1 microsecond off compared to the true time, then an error of 300 meter would be introduced when calculating the distance between user and satellite. So you can understand that why this 300 meter is there, because of the duration length of the chip. So 1023 is the chip length, and it gets repeated every 1 millisecond. So I'm talking about 1 microsecond. So it will introduce around 300 meter of error. We can see that if 1 microsecond of error is there, how much disaster we can go. We are talking about some centimeter level of accuracy these days, and if our time is not properly synchronized, we end up in tens of meters of error. So to solve this problem, we have to know the user clock offset with regard to the true time or the satellite time. Correct. So that's the only way we have to get it resolved. So considering, let's say consider a simple trial iteration case where we have measurements from three satellites, R1, R2 and R3. These are simple, the difference between the transmitted time and the receiver time from three different satellites. Now, so in this case, we have three observations and we have three unknowns. Those three unknowns are nothing but your receiver position XYZ, right? Because satellite position anyway, you know, you have decoded it from the navigation data. However, for the receiver position, you are not aware. That is what our intention to calculate. So 3 unknowns are there and 3 observations are there, you can easily solve it, right? Now add one more variable because we wanted to find out the offset with respect to the satellite time. So let's say we add one more variable, which is user clock offset dt into the user time, and rewrite the equation as tr plus dt. This dt is nothing but the clock offset minus ts. So this is our new equations, right? So now we have to solve this, definitely one more unknown comes into picture, right? So in that case, we need 4 observations. So the problem is solved now. So if you have 4 unknowns instead of 3 unknowns, then why not adding one more satellite? So if you have 4 observations, 4 unknowns, bang, you can solve it, right? So minimum 4 satellites are needed to determine the user location. What if we have more number of satellites? 4 is what we understood, that is a minimum requirement. But what if we have more number of satellites? Will it be a problem? No, actually not. So by more number of measurements, we can formulate a nonlinear least square problem, and we can solve it for using any method like least square, traditional least square method, or a weighted least square method, or even using Kalman filter, we can solve it. But it becomes a non-linear equations. So definitely before solving it, we need to linearize that equations, and then we have to solve it. This is all the basic of GNSS, which I hope earlier also might have been covered, but just a quick overview. Now coming to the software defined radios technology for GNSS receiver, right? So what
Sir,
is this? Yeah.
sorry for that. So, somewhat getting a resound. Can you check from your end, sir?
Oh, internet issue.
No, not an internet issue.
Now is it fine?
Little bit.
Is it fine now?
Okay, sir. Fine.
Okay. So software defined receivers are the approaches where uh, we use software tech to design the receivers, whereas most of our baseband signal processing will take place in software. However, you might have seen most of the receivers which are available in the market, they are all hardware based receivers. But there is some limitation in terms of the hardware receivers compared to the software receiver that in my upcoming slides I will be trying to discuss. So just to understand that what software radio gives a benefit on top of a hardware receiver is that it is built build flexible radio systems which can support multi-system, multi-band, multi-standard, and it is completely reconfigurable and reprogrammable by software itself. So that is the benefit of using a radio. So it is reliable and flexible receivers. Why we are saying that mm, reliable? Because okay, let us discuss about what is the flexibility means over here. Flexibility means that, let's say today now we have some 5 6 constellation, right? Tomorrow one more country comes up with their own constellation, or uh, some country introduce new set of satellites. In that situation, your receiver should be capable of taking the upgradation of all those changes, right? So on the fly we can reprogram the receiver. That feasibility is provided by the software radios. However, in case of hardware receiver, altogether entire hardware needs to be changed, because um, considering if the hardware has been designed only considering the present situation. So all the way that the code generations are done, then how to take the variables, everything needs to be changed. So the entire hardware, so it is a very costly affair. So software receivers are more feasible. They give that feasibility that anytime, any moment of the time, you can actually reconfigure, rechange your algorithm, because most of your baseband processing is done in the software itself. Then why software? Because I'll just give you a small glimpse of the current scenario. So existing GNSS receivers are implemented in hardware, and most of them have their own proprietary design, like for example Java positioning, Trimble, Novatel, Thales, Topcon, Septentrio, and also some chip manufacturing like Broadcom, Qualcomm, ST Microelectronics, Texas, Ublocks, then Accord. They have their own silicon, their own chips are there, and they have designed considering the signals they wanted to support. Right now, tomorrow if something comes, they might have some of the chips might have the capacity to handle it, but you never know what kind of changes will be introduced in future. So their main intention in the market is like to compete with each other, and the competition is based on that how much power each of the modules are consuming and the miniature form of the chipset. So the smaller the size, the reduced cost, it will be in mass production, because mass production will be done, the cost of production as well as the selling will be uh, can compensate over there, right? But that has some limitations. What are the limitations? The limitation is that the internal parameters of that receivers cannot be changed. So for example, if someone wants to do some research, in terms of research only, basically software receivers are much more useful. So in that sense, they cannot uh, deep dive inside the algorithms, because they are all hard coded over there, right? The firmware is already dumped in that processor, so you cannot change anything. That flexibility is not there. However, in case of software receiver, any moment of time you can actually change the algorithm, right? And you can do a lot of custom applications, you can develop it for that. So on the right hand side, I have listed out one small table for a quick comparison, where upgradable point of view, you can see that the hardware, they have a fixed platform. However, in case of SDR, they are reprogrammable, reconfigurable. Then acquisition is basically the stages of the signal processing in GNSS receiver. So in case of a hardware, you have to be bounded with serial search acquisition. Means convolution in the time domain only you can do, because if you want to do in the frequency domain, definitely you need more set of correlators. More set of correlators means again the design will become bulky and more cost, right? However, in case of SDR, you can actually adopt for an acquisition method which is straight away based on FFT, fast Fourier transform, right? Parallel frequency search you can do. So those benefits are there, because the entire load will be pushed on to the CPU, right? And CPU is computer. However, in case of a hardware receiver, the CPU is very limited. The chip is having the CPU, right? So that is very limited. It has a limited capacity to do activities. However, in case of your PC, you have tremendous capacity to do all these activities on. Let's take an example that if your PC supports GPU processing, then you can even do faster. These days software based simulators are in the market, right? So what this simulators are, they're doing the same approach. Everything is in software, only the radio part is hardware, but they come with GPU because they want to time synchronize. So that is what these days people are coming up. So earlier we never thought of having a simulator which is completely software based, right? These days it is software based simulators are also available. Now tracking more efficient in terms of hardware, because yeah, that is more reliable, because your PLL and FLLs are implemented in the hardware. Your VCO, NCO, control oscillator, they are all in hardware. You just need to program them in software. Then power consumption, less power consumption. That is the main motto of most of the chip developer. Um, and cost effectiveness, because more the hardware, more the cost. Lesser the hardware, less cost. So that is what the intention most of the commercial market people have. So I hope we just got an idea about what is the difference, basic difference between hardware and software, and why we look forward for software receivers. So it all started from 1995, when the software radio approach took a peak in the market, and people started looking more into this domain in 1996, when the first publication of GPS SDR was published by Dennis Akos. So later on, his thesis was available, which was talking about more on the real-time software receivers, because the perspective also is there that software receivers are not practically real-time, because it's very difficult to manage. How will you do a practical real-time software receiver? But it is, these days it is not an impractical task. It is very much doable. You just changing entire hardware, limiting it to only the A to D converter, and then rest everything you are doing in software. So later on, based on their initial publications, people started, different research groups started their work, and by the time I have listed only 2022 papers, because after that GNSS receiver development is not no more a research area, because it's receiver development only. uh, Using the receiver you can do much more further in that direction. So people also introduced GPU based correlations. Then they have introduced the signal of opportunity like 3G, Wi-Fi, 4G, WiMAX. These type of signals they have introduced to support the actual satellite signals. Okay. So coming to the architecture. So before that, I need to also discuss about what is the key fundamental principle of software defined radios. So the idea is move the analog to digital converter as close to the antenna as possible. This allows us to digitize the signal early, reducing the analog complexity. Secondly, use a programmable processor to handle the signal processing. This gives us the flexibility and reconfigurability in how we process the signal. Right. So in this figure, you can see that a typical software receiver will look something like this, where the only hardware part would be your antenna and the front end part. Once you get the digitized IF signal, entire right hand side processing, which includes your signal acquisition, signal tracking, PVT estimation, everything, the baseband processing typically will be done in software. So it comprises of the antenna. The front end begins with the antenna, where the incoming signal is captured. Then it is passed through an low noise amplifier to amplify the weak signal with minimal added noise. Then the local oscillator will mix, producing an intermediate frequency. This intermediate frequency is then digitized using an ADC, and that is what your input goes to a software receiver. After digitization, we enter into the digital signal processing part, that is the chain of signal processing, where first stage is your signal acquisition. So briefly I will talk here. In details I will talk in my later slides. Signal acquisition is the stage where we are detecting the presence of a signal. Signal tracking means once you have detected that, okay, out of these many satellites, these are the satellites which are visible to my antenna. Right. Now, continuously you need to align with that signal's frequency and phase. Then only that procedure is done in the signal tracking. And it is a continuous process. Next is your PVT estimation. So PVT estimation is the last stage of the baseband processing, where once you have acquired, once you have tracked, you're continuously in tracking, then you generate the measurements. Using that measurements, you finally compute your position, velocity, and time. So that's how the entire baseband processing is comprised of. In addition to the navigation decoding, it also extracts some useful navigation data, which are also used in many form. Like for example, if I give you a quick example, one is definitely for improvement of our position, that is corrections which are being transmitted by the satellite, like ionospheric corrections, then any time corrections, UTC time correction. Those corrections also being part of the navigation data, but they are not the primary navigation data. They are part of the secondary navigation data. That is one thing. And apart from that, this also helps you to decode some useful information in terms of like emergency signals, SOS signals, which the government wants to tell to the citizen that there is an emergency, like tsunami is there, or there is some major activity is happening, and the government wants to inform the users. So this is the way they can actually transmit that information. There's a provision of different SOS message, emergency messages being transmitted, that if your receiver is capable of decoding, it can decode and get that information. Okay, there is some emergency. This is one kind of extra information which can also be embedded in part of the navigation data. Now coming to the bottom part, where we can see that we have scaled it like how the processing rate and level of flexibility. So you can see that the ASIC, FPGA, microprocessor, assembly language, high level language, C language basically, and then simulation based languages tools are there. So it basically tells that the processing rate left to right is the high to low. If you go from left to right, it is from high to low, and in terms of flexibility, right to left is low to high. So flexibility in ASIC is low. However, in case of microprocessor and simulation tool, it is quite high. So ASICs are ASIC based design. FPGA offer a high speed but low flexibility, suitable production grade systems. Microprocessor using assembly or high level languages provide a balance between the performance, because they come somewhere in between. On the far right side, the simulation tools offer maximum flexibility but limited real-time performance. So here comes the idea of R&D. People try to do whenever there is a simulation term comes into picture, people think that okay, R&D means only simulations. So that's what the idea. So more the right hand side, if you go, it is like they are used for R&D purpose. So basically, the conclusion, or I would say the summary of this is discussion is that the SDR moves the signal processing from hardware to software, providing a flexibility, reconfigurability, and future proof platform for radio systems. And they are ideal for applications like GNSS, communication systems, and many more. It's not only that the SDRs, software radios, are only restricted to GNSS. Most of the communication devices these days are coming based on the SDR only. So they have a wide application. Okay. So now let us discuss step by step each of these stages. I would be like to discuss more in details. So starting with the front end. So front end, as we discussed, it comprises of the antenna, LNA, local oscillator, and ADC. So if you see this LNA, ADC, and LO all together as one unit, separated from the antenna, so there are multiple options available in the market these days. So starting from our own company's chip, that is GNSS RF chip. This is the Accord's in-house developed chip. Then we also have this RTL dongle. Uh, Third one is record and replay. It's a LabSat company front end, where you can actually record the signal and replay back in lab. So basically, it's very flexible. Even during my research, I used to use this LabSat receiver, where you can easily carry. It comes along with a battery inside that module, and you just need to have one antenna and this device. It's a small device only, and you just carry. You record the signals. Memory is there, battery is there. Record it, come back to the lab, replay it, and then you convert that signal into digitized signal, and then do your software processing. Then we have on the right, extreme right, the NI National Instruments USRP. They have a wide bandwidth coverage. However, it's a little bit costly. Then we have this IP solution, Japanese company, it is IP solution. Then there is Blade RF. Then SIG is also very old. If RTL dongle, this used to be very much familiar. Now NT Lab also has their own RF front end, which comes with 4 terminals, so you can actually connect 4 different bands over here. That feasibility is there. I'm not sure about the exact technical details of this board, but just to give an idea, these are the available. Then Maxim 2771267 is a very widely used RF modules. Uh, most of the commercial receivers would, I would say, mostly they started their journey with this Maxim receiver. It is basically from the analog devices. And then also Pocket SDR. This is also from Japan, I think. Yeah. So these are the possible options available in the market if someone wants to start their journey. I have tried my best to recollect all the informations. If someone wants to start his or her journey in this area, where to start from, how to get it, all those details I try to put into my presentation. So these front ends are available. They have the capacity to give you the IF signals, and then using that IF signals you can actually process in the software. So only this is the hardware you need, this RF front end and one antenna. Rest everything you can do in the software itself. So yeah, so all those descriptions only have been provided. So I have talked a little bit more about this. Okay, there is a comparison in terms of bandwidth and frequency it can support. Okay, so this RTL dongle is having the least bandwidth, 2.4 megahertz. Okay, okay. So, but it can support L1 and L5 frequency. Yeah, it can support both frequencies, L5 and L1. Okay, and the options for ADC is 8-bit ADC, and then you have this Blade RF. Okay, 56 megahertz bandwidth is there, 47 to 6000 megahertz of frequency. The bandwidth is quite high, and okay, USRPs, yeah, definitely. So these are the possible. So I have also tried to list out the cost associated with this RF front end. So the least costly is your RTL SDR, right? Now Maxim, basically it is only the chip. I'm not sure whether it has been obsolete or it is still present in the market, but this is a very good RF front end. If someone wants to use it, they can buy it from the online website, and then they can make it their own PCB and they can use that directly. Or best feasibility would be using this NT Lab or Blade RF. They are not that costly. Blade RF would cost around some 80,000, 40 to 80,000 rupees, I believe so. USRPs are quite expensive. Okay. So now once you are familiar with the RF front ends, for where to get it and what kind of RF you are willing to use based on what kind of application you wanted to support. Now coming to that realistic experimental setup, that how do you collect the data and what are the minimum requirements to collect the data and then directly jump into the processing part, right? So you need an active antenna basically. If you want good signal strengths to be captured, you need an active antenna. However, in a clear open sky, a patch antenna would also help you. Then if you are using an active antenna, definitely you need a bias T to power up the antenna, and one RF front end that we have already discussed. So we basically, for software receivers, the distance, this length between the antenna and your digitized IF, we try to keep it as minimum as possible. That's the idea. So there should not be any propagation loss, because propagation losses through a wide medium is exponential on the exponentially depending on the cable length. So much higher than those who through radio transmission, right? So shorter the cable lengths of just a few meters or even less than a meter, the impact of using a high or low loss coaxial cable may be negligible. However, if someone wants to also buy a coaxial cable of good quality without any significant attenuation in the signal, some suggestions from my side, that is the RG58 or RG214. They provide approximately some 30 dB of attenuation per 100 meters, while these values goes even down to 15 dB per 100 meters for a new generation RF coaxial cable named as LMC 400. So internet, I got this table below. You can see that. So if 400 megahertz is your frequency of support, so RG213 losses is 4.8 dB per 100 feet. However, in case of LMR 400, the attenuation is 2.5 per 100 feet. So they are definitely better. So this is just an idea that what kind of cable you need to buy, what kind of antenna we have to buy. Now, coming to the signal structure, right? So this is all about the hardware. We have understood about the front end, now everything. Now we need to understand the signal structure. What exactly we are going to decode, what exactly we are going to process, that we need to be very much clear. So signal, starting with the signal structure, basically a GNSS signal is constructed or is generated by multiplying three major components. One is your carrier, which is at 1575.42 megahertz. This is L1 frequency, 1.5 gigahertz. And we have a pseudo random number code x of t, which basically the job of this is to spread the spectrum. This is a CA code at 1.02 megabits per second. And third component is your navigation message, which is the information, right? The actual information which is being transmitted from the ground station to the satellite, all about that information about the satellite health and everything what we discussed earlier in our slide. So that all informations are included in this navigation data. So all together these three components forms your baseband signal, which is your x of t, d of t, cos 2 pi ft. So this is your GPS signal, and the modulations allows us to multiple satellite to transmit at the same frequency but remain distinguished by their unique PRN. So each and every satellite has its unique PRN. Their modulation is used BPSK. However, it is a code division multiplexing technique where each of the satellites are being associated with a different code so that it can be easily identified. So BPSK, as I said, binary phase shift keying is the modulation scheme which is being used, that which basically maps the symbol to either +1 or -1 amplitude. So before that modulation, the onto the carrier, the modulation navigation data, which is your D of t, is multiplied by the spreading code. So by multiplying which this you can see that the D of t is 50 bits per second, right? It's a very low rate. So when low rate is multiplied with a high rate, basically we are talking about something, the spread spectrum, right? Uh, so the power of the bits are they are spreaded across the wider bandwidth, which enables nothing but the spread spectrum communication, or also widely known as the direct spread spectrum technique. Now on the right hand side you can see that mm, the frequency representation has been demonstrated over here. So each chip in the PRN sequence, which is 1.023 megabits per second, each of the chip of the PRN sequence is a rectangular pulse in time. So we know that rectangular pulse Fourier transform is nothing but a sinc function, right? So this means that the GPS signal has a sinc shaped spectrum with the main lobe, and multiple side lobes, right? And the main lobe width, what is the bandwidth of that is determined by the rate of the chip, that is 1.023 megahertz. So the bandwidth would be 2 by t is equal to 2.046 megahertz. So this is the reason why this explains typically the why the GNSS receiver must have a front end filters and ADC sampling rates wide enough to capture at least this main lobe signal. So that is important. So this also add-ons to one very interesting fact that since it is a spreading operation, which also increases the bandwidth, this basically helps us in enhancing the signal robustness and also improving its resistance to the interference and typically helping us the code division. Right. CDMA. Oh, once again, it is my slides are visible, right? I hope everything is fine.
Yes, sir.
Oh, it's fine. Okay. Yeah. Okay. I hope this part it is clear. Now coming to the what a receiver basically. Also, one more point I would like to add here is that in terms of security and interference rejections, why? Because we were talking about direct spread spectrum. So at the receiver, the original signal can be easily retrieved by multiplying with the same spreading code, because at the receive you know what is the PRN sequence which is being used to spread that signal at the satellite level, right? The same PRN sequence can be used at the receiver to despread that. However, let's say if some jamming signal or interference signals comes in between this your actual signal, which may not be spreaded by the true PRN sequence. So first time at your receiver level only, it will get multiplied with your spectrum, the PRN sequence. So it will get spreaded out, and your actual signal will get despreaded, right? So you can use one specific bandpass filter to filter out all the other unwanted signal, and you can only capture your signal. So this itself give you one stage of interference mitigation by the tech itself, right? You don't need to do anything extra. So the rate of spreading code and the rate of original signal, uh, that comes out to be around 10 to 60 dB. So that is the processing gain. You can say that that will help you to reject that unwanted signal. That is the benefit. Now, what receivers measures, right? So, basic measurement made by a receiver, GNSS receiver, is the time required for the GNSS signal to propagate from a satellite to the receiver. This can be obtained by tracking the PRN code modulation of the signal. Then within the receiver, a local copy of PRN, the local replica, is generated, which is continuously compared and aligned with the signal received from the satellite. And that is done in the tracking loops, right? And which provides continuous measurements of the instantaneous, what is the change in the code phase, as well as change in the frequency, which is your Doppler change. So if we have these two informations, we can actually continuously try to measure the range between the user and the satellite, because assuming they might be relative to each other, right? You might be, the receiver might be static, but the satellite is still moving, right? And also there is a chances that your receiver would be moving and the satellite is also moving. It can move in along the same direction, it can move in the opposite direction, so that relative change will be always there. So considering all those things, continuously the change in the phase, code phase, and the Doppler needs to be monitored or measured. Okay. in this context, in the previous slide, when we were talking about the digitization of here, digitization of IF signal. So what is the need of IF? Why do we need IF signal? So in GNSS receiver, typically the incoming signal is being transmitted at a very high frequency. Here for GPS, we are taking an example of L1 band, which is 1575.42 megahertz. So directly processing such a high frequency is impractical because of the hardware limitations and sampling requirement, right? To solve this, we definitely need to shift that signal down to a much lower frequency, also known as an intermediate frequency. So in this picture, I have shown you that the FL frequency is down converted to a 4 megahertz IF, and then using a band pass filter you can actually capture only that, and this is only the down converted signal, so it still have the all information, like everything. There is nothing loss in that signal. It is just a down conversion of the high frequency to a low frequency. So a band pass filter, typically a band pass filter can be applied around the IF frequency to reject the unwanted signal and the noise. Why this stage is important? And it is critical because it allows the receiver to process signal using lower speed ADCs and digital circuits while still retaining the information contained in the original GNSS signal. So still that PRN sequence, the navigation data, they remains the same, only to process in a particular hardware based system we need to down convert that. There's a provision that you can actually down convert the frequency to a 0 IF, but that can be done in case of software receiver. But in case of hardware receiver, it is not possible because you need a sharp cutoff frequency for that. Filter is required, but ideally making that sharp filter may not be possible. So that's why we down convert into some different frequency. So it is easy to capture that signal. So instead of 0. Now, on the right side, we know we have already discussed about the baseband signal, that x of t, d of t, cos 2 pi f t. That is what is the signal which we are receiving. Now, with a local oscillator where that is mixed, the GPS incoming signal is getting mixed with a local oscillator, and pure basic trigonometric maths is being applied over here, where we have cos A cos B, which comes out to be cos A plus B plus cos A minus B. So we have one addition part and one negative, the difference frequency, right? So we have two parts. One is the sum of the frequency, which is your FL plus FIF, and one is the difference, that is FL minus IFL, right? Now a band pass filter center around the intermediate frequency FL selects the desired difference term, and this gives a clean down converted signal. So that is on the right hand side, which is some power root p x of t of t cos 2 pi FIF t. So we have a down converted signal IF. So now we know that we have down converted the signal, we got the signal. Now what next we are going to do? This is the signal which we are going to process. So we use a in phase and quadrature phase approach, where the local copy, the 90-degree phase shifted version of that is being multiplied or mixed with that incoming signal, and then passed through the low pass filter, and we get the in phase values and Q values, right? Now there is also one term we were discussing so far, like Doppler. So GPS satellites have a speed of 3.9 kilometer per second. Thus, due to the Doppler effect, the frequency of the received signal may not be the original L1, but it would be the frequency, means it will be in addition to that your Doppler. Doppler will also be part of that. So assuming that on the right hand side I have given a clear picture, let's say I of t and q of t is there. Now interpretation would be that in which phase the actual signal is there, data. So assuming that both cos and sine we have to take care, we don't know at which mm, part it is actually modulated, right? So however, the delta that Doppler is associated, it is not only the BPSK signal but also the Doppler which is getting associated. So we in the tracking loop, basically what we are trying to do is we are trying to monitor the change in the Doppler. So we are trying to minimize that error. So if we are tracking, we are perfectly aligned with our incoming signal, the local generated is perfectly aligned, so then there will be no phase difference, right? So this I, since it is a BPSK modulated, so your constellation diagram, the IQ diagram, you will see only +1 and -1, right? It should be +1 and -1, 180-degree phase shifted, right? But now because of the Doppler, it will try to get change, means it will get some values. So it will try to always rotate in the circle direction, right? I and Q, it will try to get rotate. And the job of a tracking is to minimize that error. And you have to estimate that Doppler properly. That is only what we are doing in tracking. Okay, so let us take one example that uh, moving forward, that what exactly the signal strength of received signal is there and how we are going to process that. All those things will be covered here, where we know that it is the pure link budget, where PTG TGR lambda square by 4 pi square will take. So let us take one example where 30 watt is what the signal power, with a gain of 10, transmitting gain at the antenna, transmitting antenna. We do not have any receiving antenna get assumption, and this 30 watt of signal power is being transmitted on a carrier of L1, let's say 15. So the bandwidth of that, sorry, the wavelength would be 0.19 meters or 19 centimeters. Sorry. So you can see that this and the distance between the transmitter and receiver, we assume that it is 20,000 kilometers. So 20.2, 20,000 kilometers, 20 into 10 to the power 6. That is what the R basically we have. So you can, to give a rough idea that what is the signal strength basically we are receiving from a transmitter which is located 20,000 to 30,000 kilometers away from us. So it comes out to be 1.68 into 10 to the power minus 16 watt. So you just imagine that how weak that signal is. So in terms of dB watt, it comes out to be minus 157.74 dB watt. That is the level of power we are receiving in case of GNSS also. So let us assume that the power of current GNSS signal as received on the earth is would be around minus 160 dB watt. So what is the signal power, signal to noise ratio? The signal power by the noise power. Density would be your Boltzmann constant by the effective temperature. So effective temperature at a room temperature of 290 Kelvin. So all those calculations are done. Boltzmann constant, if you multiply, you'll get some value, and then let us assume the bandwidth is 2 megahertz. So it turns out to be minus 141 dB watt. So the signal to noise ratio would be minus 160 dB watt minus of 141 dB watt. So it comes out to be minus 19 dB. So this is what the signal power, signal to noise ratio we are talking about, GNSS signal. So it's a negative SNR, where all communications we are talking about the positive SNR. Here we have something which is negative SNR. This brings to a conclusion that we need something that we need to bring this signal above the noise level, right? Because this negative 19 dB indicates that everything is buried below the noise floor. and that is because of the spread spectrum. Basically, it is the reason, it is the consequence of the spread spectrum, I would say, rather. So here comes the concept of correlations. Why do we need correlation? So this is the reason why we need to correlate, because the signal power of the received signal is so small that it is simply a noise. Everything is buried below the noise, so we need to bring it up. So we need correlation. So we need a replica to raise it above the thermal noise level. So if we want to calculate the carrier to noise density, that comes out to be signal power by the noise density. This carrier to noise density is one term which is widely used in terms of GNSS. Why? Because SNR is associated with bandwidth, right? So different receiver front end will have different bandwidth. So we need one generalized solution where we can tell that, okay, this much is the true signal strength we have received. So in terms of that, one common indication should be there, which will tell us that, okay, this is what the signal power receiver A is receiving and B receiver is there. So there should not be any bandwidth concept. So there comes this carrier noise by the noise power density, which is nothing but SNR into bandwidth, where bandwidth is 1 hertz. So in that case, it turns out to be minus 160 minus 204. That is basically only the Boltzmann constant into the effective temperature. Bandwidth is not there. So N0. So that term is minus 204. So it comes out to be 44 dB hertz. So if your signal is minus 160 dB watt, you should see a signal carrier to noise density of 44 dB hertz. It's not dB per hertz, it is dB hertz. This is the theoretical value. However, because of the different gain and the noise level of the receiver, thermal noise of the receivers, in case of hardware receivers, it may fluctuate between 42 to 44, right? We are talking in dBm. If you want to convert that in dBm, it will come around to be minus 130 dBm. Okay, one very good presentation is there, which says that if your signal power is, let's say, minus 160 dB watt, and your noise power is minus 20 watt, so then your carrier to noise density will come out to be 44 dB hertz. In that case, if your bandwidth is 2 megahertz, that typically uh, involves adding 63 dB, additional 63 dB, so which comes out to be minus 141 dB watt. So the ratio becomes minus 19 dB. So signal, so if you try to correlate, obviously the noise will also get correlated. So on the left hand side, minus 111 dB watt is the noise correlation, 30 dB approximately gets added to that, and signal correlation around approximately 60 dB. So after post correlation, you get a signal of minus 100 dB watt. That is what the after correlation. But before correlation, it is minus 160 dB watt. So that's what we can say, that correlation has a significant role in bringing the signal above the noise floor. In terms of signal processing, these would be the stages of the entire receiver, where initially whatever the IF data comes, it has to pass through the acquisition, tracking, navigation data synchronization, then decoding of navigation data, and finally pseudo range computation. Using that pseudo ranges, you will compute the position. So acquisition, a brief introduction already I have covered, that it is to find out or locate what are the satellites which are visible to you. Once you know the course value of those, you try to track them, keep an eye and refine them. Why? That also I will tell. Why? Because then tracking can be of two parts. One is code tracking and carrier tracking, because we have both the things. Code is also there and carrier is also there. So carrier tracking is typically done by means of FLL, phase lock indicator, phase lock loop, or frequency lock loop, or a combined form of both. And code tracking is done using the delay lock loop. Once you have done this, carrier tracking is to track the Doppler changes, and DLL is to track the phase changes in the code. Typically, the DLL is being implemented by the normalized early minus late discriminator. However, the FLL is, as I said, it is frequency or phase lock loop, or sometimes it could be your FLL assisted PLL. In terms of acquisition, there are different ways to do that. In case of hardware, they generally do the convolution in time domain. However, in software receiver, we have the feasibility to do that in frequency domain directly. So more details on the acquisition side. We can take a quick break, sir. Hello.
Sorry, sir. Sir, we can take, sir. Right, you can join in 7:30 link, sir. Meanwhile, I need to take some photographs here.
Okay.
Okay. So we can join in 7:30, sir. You. And so for all the participants, can you switch on your cameras, please? We need to take some photographs, as I already. Sir, can you stop sharing, sir?
Oh, okay. One second.
Please, all are requested to switch on the camera. Yeah, Vishnuvardhan sir and Srinivas Rao sir. So please switch on your cameras. Cake. Yeah, thank you all.
Yeah, thank you.
Madam, can you Avita madam, can you share the feedback link and attendance link, madam?
Yeah, yes, sir. I will share.
Yeah, all of you, you can join in the next session. It starts around 7:30. So I have shared the link, and again, I'm going to share the link in the chat, the WebEx chat as well as the
Sir, I
WhatsApp
will
link.
share in this chat or next session chat.
You can share here as well, madam.
Yeah, in this session.
In this session, madam.
Okay.
And also, when next session starts, at the time also you can post, madam. This is the link. So with this link, you can join next session.
Our camera, sir.
Yes, madam. Thank you, madam.
Thank you. Thank you.
Thank you. You can join in next session. So I'm going to close this. So I think everyone got the attendance. Madam, you have not shared attendance link here. Okay. I think link is here. It is posted. You can mark the attendance as well as feedback. So the same sir is going to take for the next session as well. I'm going to end the session. You can join in the next link. Thank you all.